Hello everyone and welcome to this Men&Mice webinar. My name is Peter Pettersson and today's webinar is focused on namespaces for local networks. This is the first webinar of three, so we have a triology here, Karsten, from you, focusing on resolution, DNS resolution on local networks. That sounds interesting. And I just wanted to remind everyone that we are recording this webinar, so if you drop off for any reason or don't get to the next webinar, you can always find these recordings at our website, a few days after the webinar and so on. So having said that, Karsten, the audience is yours.
Thank you, Peter. Hello and welcome, everybody. So today we will talk about namespaces for local networks. And the reason why we talk about this has a reason. There is something happening, which is a little change in some program a lot of people use, which is the Chrome browser. And we've taken that change that happened there and the fallout, what follows from the change, to talk about good solutions for name resolution in local networks. So what's happening here is that in one of the upcoming Chrome browser versions, there will be high HTTPS strict transport security enforced for the .dev top-level domain. You see here the change in the software versioning control system from Google, and it's not currently in the version that you can download, not in the normal version of Chrome, but it's already in the beta version, in the so-called Canary version. So what does this change do? It enforces HTTPS, that is TLS encryption, for all domains that end in the .dev top-level domain. And here we have two Chrome browsers side by side. On the left side, we see the current version, and on the right side, we see the Canary version, the future version. And you see if website.dev is being resolved and looked at with the old version, with the current version, it just works. It gives the website, and with the upcoming version, it gives an error message. So what happens here is Google owns the .dev top-level domain, and they own it for quite a while now. I think 3 years from now, and so they are able and they have all the rights to make such policy decisions for their top-level domain. It just happened that a lot of developers, especially web developers, have used .dev for their internal testing domain. So they created a local namespace in their test environment and created one or more domain names with their test web servers that end in .dev. And now these domains cannot be used freely anymore. These even they are internal. If the web developer tries to test the domains with the Chrome browser, they wouldn't work without HTTPS. And in order to use HTTPS with Chrome, you need also a fully good TLS certificate, which you don't get because the .dev domain is currently only used by Google. There's no delegations outside Google, so there's no certification authority that will give you a certificate for any .dev domain because it's just all owned by Google. Quick sidestep: what is this HSTS? It's short for HTTP Strict Transport Security, and it's an internet standard, RC 6797. It's usually a header that is stored on a website that tells the browser whether that domain and all websites on that domain need always be secured by encryption, by TLS encryption, that is using HTTPS. So once a browser has visited a site that sends the HSTS header, the browser remembers that this domain needs to be TLS secured And on the next connection, if then the web server pretends that it cannot do any encryption, that is then a sign of a man-in-the-middle attack, and the browser will refuse to go there. HSTS is a good idea, and it should be enabled for all websites, at least for all production websites. You can test with this testing website securityheaders.io. You can test any domain name and any website, whether that website actually sends the HSTS header. So here we see the strict transport security header being shown for dnsworkshop.org, and that is actually the configuration on the web server for this header. It's the strict transport security header, and then there's a max H value, which is the time in seconds that from the time that the browser sees this header in the future, this domain is guaranteed to be HTTPS secured. So Google owns the Chrome browser, and they own the dev top-level domain. So for them, that makes really sense to ship the Chrome browser with a preloaded header for strict transport security for their own domains, which today includes not only .dev but also .foo and .google, which are also two other top-level domains that are owned by Google, and they also ship with preloaded headers in the Chrome browser. But the Google Chrome issue with web developers is just one of a larger problem. We see many networks where administrators or developers use local domain names in their local networks that are not owned by them. Just last week, I visited a larger company, and they had two of these names that are listed here, two of these top-level domains listed here in their infrastructure being used. Something like .lane, .lan, .company, .media, .webdev, .serverinfra, .box. All these names are risky names because there can be collisions with new top-level domains. So using a seemingly unused DNS top-level domain for internet networks is really a bad idea, because with the new top-level domains coming out from ICANN, sooner or later there will be name collisions because that top-level domain is being used in the internet. So what can we do? Now we have multiple choices. The best choice probably is, and we talk about that in detail in a moment, is to use a subdomain of a delegated domain. That is, you buy a domain in the internet, you don't use it in the internet, but you use it only internally. We can also use the reserved top-level domains or reserved second-level domains, and we talk about them in this webinar as well. Or we can use name resolution other than DNS, like multicast DNS or link local multicast name resolution, or even peer-to-peer name resolution protocol, PNRP. And we talk about them in the two other webinars that follow this one in the trilogy. So option one is to use the subdomain of a delegated domain, which means that you own a domain in the internet. And if you own that domain name, like a second-level domain, somename.com, somename.farm, or you can use any of the new top-level domains, doesn't matter. But what's important is, once you own such a domain, all the namespace below, all the subdomains, all the subdomains, and everything below is owned by you. And you are free to use these names, and nobody else can catch that name and can use that in the internet. Such a locally used name should not be reachable from the public internet. So even though you own the name and is registered by some registry in the internet, you just don't use it for production work in the internet. It's only used then internally. So here's an example. In this example, we use the lan.example.com. And example.com is one of these, in this example here, is a domain that is registered by the owner of this network and is not being used in the internet. And if a client that sits in the internet is querying that name lan.example.com. It goes to a DNS resolver, and that goes, after following the delegation, goes to the authoritative server for example.com, and the answer is NX domain because it's not used in the internet. But if we look in the internal network, there we have the internal DNS resolver, and the internal DNS resolver has either a forward or a stop zone that points to the authoritative server for lan.example.com, or even subdomains of that, like hr.lan.example.com. So if the query for hr.lan.example.com goes here from the client to the resolver from its configuration knows where to send the query to, and the answer is coming back, and that queries don't leave the internal network. It's all internal, never seen outside. So that is how we use the subdomain of a delegated domain. Later in this webinar, I will present configurations for both Unbound and Bind9, how to implement these kind of internal domains. But before we do that, we have a look at the second option, which is to use a domain reserved for local use. So the IETF reserved a number of top-level domains that should not be used in the internet, which are reserved for local or private use. They were originally defined and standardized in RFC 2606, reserved top-level domain DNS names, and later then updated in RFC 6761, the special use domain names, which that RFC makes more clear that these domains, while they are not used in the internet, should not be treated any special by software. So it should not be treated special by like web browsers or mail clients or DNS resolvers. From these RFCs, we have 4 domains that are reserved. The first is .test, which is for test deployments. We have .invalid, which is or should be used for configurations which are broken by design. If you want to prove some problem, some misconfiguration, then you can flag that with the .invalid top-level domain to make clear that this misconfiguration is intentional to prove a point or to test software or something like that. .example is for documentation and example work, and .localhost is the canonical host name for all machines that resolve into the loopback address. So for internal development systems, like if you are a web developer that needs to test local software, the .test top-level domain and any subdomain of that would be a good choice to use. So here's an example how that could look like. Here we have a client asking for www.1.webdev.test. That query goes out to a DNS resolver. That DNS resolver has either a forwarding or stop zone pointing towards the authoritative server webdev.test and beta.test. And here the query goes to the webdev.test authoritative server, answers coming back, and the client can connect to the testing web server. Another option, which is rather new, is the domain home.arpa. Home.arpa is reserved for the HomeNet Control Protocol, and HomeNet Control Protocol, in short HNCP, is a new protocol from the IETF that is being used to automatically configure home networks with multiple subnets. Now, as more and more networked machines populate the home networks, like we have the TVs, we have internet radios, we have Amazon, Alexa, Google Now, and Siri, and a lot of other devices that populate the wireless. Users and owners of these machines might want to separate these machines into separate subnets, like having the TV in and all the entertainment systems in a different subnet from the computers that are used for work, for security reasons, because a lot of these Internet of thing devices. They never get updated, and there might be a security risk. So separating them in multiple subnet is a good idea. However, not everyone at home is a network engineer. Not everyone at home knows about routing protocols and how to do a segmented network. And the home net control protocol is a way to have multiple segments automatically configured, have the routing automatically configured, and everything plug and play. And this plug and play network works with the domain home.rpa. The home.rpa domain is being reserved to never be used in the internet. It's currently not an RFC, it's still being worked on, so it will be an RFC later, maybe next year. And there is an internet draft on the special use domain home.rpa, which I have linked here that you can read what the home.rpa domain is all about. So here's an example how this could be used. Here's the DNS resolver with home.rpa local zone. So we don't have any delegations here, just one DNS resolver. And the query that goes to www.dev home.rpa is directly resolved on the DNS resolver without talking to the internet, without talking to any other DNS server. Answers just directly coming back to the client and is being resolved. So that was the second option of using some namespace for local domains that don't collide with the internet. We have more options like the link local multicast name resolution that works in Windows and modern Linux. We have the peer name resolution protocol, which is technically very fascinating. I will show that in the next webinar. And we have multicast DNS that is working for macOS, iOS, Windows, and Linux. So it's available for all the major operating systems. And that will be the topic of the third installment of this webinar series. Now we have a look on actual configuration, how to create a local zone with Unbound. Now you might know Unbound as a fast and lean DNS resolver that is available for almost all operating systems and can be downloaded from https://unbounce.net. Also, it is in the packet managers for almost all Linux systems, and in macOS you can find installable. For macOS and Windows, you find installer on this website. So the main purpose of a DNS resolver such as Unbound is to resolve names in the internet for local clients. However, Unbound has some limited authoritative functions, so it can also serve zone data. It's not a full authoritative server. The authoritative functions that are in there are aimed for smaller networks. I would say this setup that I present here is recommended for networks that have less than 100 DNS clients. The other design that I will show later based on point 9, that is then for larger networks. Benefits of using Unbound for local zones is it's really simple setup. You only need one type of software, which is Unbound, no other DNS server there, and you have quite fast response times because it is directly between the client and the DNS resolver. No other machines need to be asked. The downsides of using Unbound in this configuration is there cannot be DNSSEC security for the local zones because DNSSEC validation requires that you have at least 2 machines, one hosting the zone and one validating the zone. However, because we are all in the same network here, this might be okay because in the same network, if the network is trusted, there is little chance for an attacker to spoof the data. No DNSSEC is only true for local zones. If there are internet zones that are DNSSEC signed, of course, DNSSEC validation will just work normally. And the second downside is that there's no automatic provisioning of multiple servers, of multiple Unbounds via zone transfer. So if you have more than one DNS resolver for a failover and resilience reason, you have to duplicate the configuration manually or use some configuration provisioning system like SaltStack or Ansible for doing that. So here's the design. We have a client in the internal network. We have a DNS resolver with the home.arpa local zone configured. And we have some names in the internet, the root zone, .com zone, example.com zone. If the client asks for something in the home ARPA domain, that is directly being resolved from the Unbound running on the DNS resolver. So answer is coming directly back to the client without reaching the internet at all. If a query is being sent for example.com, which is the name that is in the internet, then the resolver goes out, does the usual recursive name resolution here. Answer is coming back from the authoritative server for example.com and is being given back to the client. This is the configuration for Unbound, and this can be stored in the Unbound configuration directory. It must be stored in a file that ends in .conf so that Unbound will pick it up. On Debian Linux, it's in etc unbound unbound.conf.d. First, we unblock the LAN zone and the insecure LAN zones, which enables Unbound to resolve these local names and also don't try to validate to DNSSEC validate these zones because they cannot be DNSSEC signed here. And then we have with multiple local data statements the resource records in there. So you can build a zone file just like a normal zone file in any DNS server. You just write local data colon there and enclose the resource record in double quotes. So here we have the SOA record, the NS record, which points to the NS record should point always to the Unbound instance itself. And then we have IPv6 and IPv4 addresses. Of course, you can use all the other resource records that are supported by Unbound, which are almost all the resource records that are available. So SRV records, MX records, all work. The next configuration example is about larger installments, here with Mind9. And here we recommend to split up the local zones on their authoritative servers, separate from the resolvers. That has multiple benefits for larger zones. It also is easier to administer. On the next slides, we show this example design based on Mind9, but the same design can be implemented with other DNS servers as well. So you can use Windows DNS, Power DNS, or any of the others that are available. It should work with any normal DNS server out there. So what are the benefits of this setup? It's higher resiliency because we don't have a single point of failure. We have multiple machines for the resolver function and for the authoritative function. We have automatic load balancing and failover between the authoritative servers that is delivered by the DNS protocol. So we don't need to have any load balancing software running there. It's all in the DNS protocol. We have DNSSEC signing and validation possible. So if we want to secure the local zones, that is possible as well, but it's not mandatory, it's just optional. And the zones can be kept in sync with regular zone transfers, so it's easier to maintain across multiple machines. And we have options for better monitoring and logging because we can separate the authoritative traffic from the recursive traffic. So this is the setup. Here we have the internal network, and now the resolvers are not in the internal network. The resolvers are in two separate data centers. There we have authoritative server for home.arpa zone or the locally used delegated domain. And then we have DNS resolve with a stop zone for home.arpa. And here first the client is asking example.com, which is the domain which lives in the internet. The client chooses one of the two DNS resolvers. Here it chooses the data center 2 resolver, asks for example.com. That resolver checks the stop zones, doesn't find a match, so it goes out and does normal name resolution in the internet, asks the root name server, com name server, reaches the example.com authoritative server, and from there we get an answer back. That answer is being cached and goes back to the client. So that is normal DNS name resolution. But if we get a request for the home.arpa domain, www.dev.home.arpa is the query here, that again goes to data center 2. And because we have the stop zone configured there, that is being redirected to the authoritative server that is in that data center. Answer comes back from that authoritative server being cached and being sent back to the client. To build such a configuration, here we have the bind configuration file for the authoritative server. On the authoritative server, we disable recursion because it's a pure authoritative server, so we say recursion no in the option block. And then we have a normal master zone. Nothing special here. It's the zone home.arpa, type is master. It has a file where the zone data is being stored, and optionally, we can have inline signing and auto DNSSEC maintain if we want to have everything DNSSEC secured, but that is not required. We could also skip that and have it as an unsecure local zone. And that is the zone file. It's just a normal zone file, as you might know. SOA record, NS record, pointing to the authoritative server itself, and then we have some IPv6 addresses, IPv4 addresses in here. What's a little bit special is the resolver server. The resolver server has an allow recursion access control list that lists all the clients. Now that access control list, clients here should list all the internal networks that should be able to use this resolver and create the names. Then in case that you use DNSSEC, because a local domain cannot be secured from the internet route, because it's not delegated from the internet route, you have to use your own managed keys here. And that would be for home.arpa and everything below that. So you create the key pair on the authoritative server, the copy over the public part on the recursor, and you configure the public part for home.arpa on the resolver, and that enables the validation here. And then we have a stop zone for home.arpa. It has its own file, home.arpa, and we list the IP addresses of the masters. And these IP addresses are the IP addresses of the authoritative servers in data center 1 and data center 2. With this stop zone, the resolver will make contact to the authoritative server, will fetch the SOA record and the NS record information, and by getting the NS record, it will learn where to find the authoritative servers. And using a stop zone is much better than having forwarding, because it works quite nicely then with the DNSSEC validation. So that was the bind configuration example. Our next training that we will have is in March. That is the DNSSEC and DANE training. That was originally planned in December, but we had to move that into March because we had already another training being booked and filled on the December slot. So if you're interested in learn everything about DNSSEC and DANE, that is how to secure the TLS, HTTPS, and email encryption with DNS, then come to this training. It is in Linux Hotel, which is in Essen, Germany. We will post more trainings in English language available then in the US and somewhere else in Europe later this year. and that trainings will also be then in next year. Our next webinar will be on Tuesday, the 7th of November, and that will be the second part of the local name resolution trilogy. And there we talk about Microsoft operating systems and their special name resolution protocols that are available, which is the link local multicast name resolution and the peer name resolution protocol. We take a look at these protocols in Windows 10 and Windows Server 2016, and how these protocols can be used to have a serverless name resolution without a centralized DNS infrastructure, which is especially interesting for local networks. And also we look deeper how interoperability is with the older Windows versions, such as Windows 7, Windows 8. And also we look a little bit in Linux, how Linux can talk with LLMNR with Windows hosts. And then the third one will be all about multicast DNS, which was originally created from Apple for Mac OS X, but it's now available in all major Unix versions and Linux, and it's also available on all the Apple operating systems as well as Windows. And Windows, it's not a native service, it needs to be installed, but we will cover that in this webinar, which will take place on Wednesday, 29th of November. And this concludes this webinar. Do you have any questions?
Well, I maybe forgot, Carsten, to mention it initially, that at any time during this webinar, guys, you can post your questions through the GoToMeeting control panel. There is a place there for questions. So let me see. There are no questions yet. So if there are questions on your mind, you can drop them in there right now. But Carsten, these are interesting times for name resolution. Definitely.
Yeah, it's especially that more and more devices need to use name resolution without extra configuration. The IETF and others, the vendors and producers of operating systems, they try to find new solutions to make name resolution more easier, more ad hoc. But of course, in a managed network, in an enterprise network, administrators want to have control over that as well, and should know about this.
Are we moving too fast or too slow on this matter?
Probably too slow, because it takes up to 10 years now to implement a new protocol really in the internet. So once it is standardized in the IETF, it takes a few years to be implemented in the operating systems, and then it takes another few years for all the computers to upgrade to the new versions of the operating system. So today, it takes between 5 and 10 years for a new protocol to really being usable on internet scale.
Okay. Well,
so like the LLMR and peer-to-peer name resolution protocol that we will talk about next webinar, they were introduced in Windows 7, which is now 8 years ago. But it is just now that we can really use them.
Okay.
Because now all the Windows XP and Windows Vistas are gone, which couldn't use them. And now we have an infrastructure, and we have all the operating systems that support these technologies.
Yeah. No. So, Carsten, there are no questions now. The audience is probably saving their questions until next round. We will have this recording available through our website and with the slides as well within a few days. So, Carsten, thank you very much for this webinar, delivering this webinar today. And I'm looking forward to the next part. Was it November? Let me see. November 7, was it?
Yes, November 7 should be. There it is.
Sounds perfect. So thank you all for attending, and have a nice day then.
Thank you. Have a nice day. See you next time.